There we go. So welcome to those who have just joined us bang on 1 o'clock. We've just got a 5-minute period where we're going to allow people to get signed in for those who've got back-to-back meetings or Zoom isn't quite behaving the way they want it to for them today. So if you could keep yourself on mute with your webcams off as well, that'd be great. We've just got a short little video about the Mbas facility that's being built next to Glasgow Airport at this moment in time. And this will just play to let you have a better appreciation of what Mbas is planning to look like. And if you are logged in and all up to speed and you want to go and get yourself a coffee, a cup of tea or a glass of water, I'd say now's your chance to do that. Thank you. There we are. Thank you very much, everyone, for allowing everybody some time to get connected today. We're going to now begin the webinar. So this is our third Mbas, which is Additive Manufacturing Business and Technology Support webinar that we've run. We're running this one focusing on hybrid additive manufacturing. So we'll be finished up around about 3:15 Greenwich Mean Time today. Just going to go through some quick housekeeping. So this webinar is being recorded and it will be made available on our YouTube channel at a later date. The chat, though, is not uploaded as part of this. Your microphones and webcams will be turned off for the duration of the session. This is just to avoid background noise. You can type questions throughout the session in the open forum just via the chat tool. Although there is the option to send questions privately to my colleague Kwaku. That's also just done in the chat tool. Just select message Kwaku privately. And following on from this, we'd appreciate if you could take some time to complete the survey that'll be sent out to you. So our webinar hosts today from Mbas are Stephen Fitzpatrick, who is the team lead for the additive manufacturing and machining team and the principal investigator on this project, as well as myself, Grant Payne. I'm a manufacturing engineer in Stephen's team, and I'm project lead on the Mbas project. So just to give you a quick high-level overview of the Mbas project, this is funded by the EU from their ERDF funding, and this has all been moderated through Scottish Enterprise, part of their Advancing Manufacturing Challenge Fund, AMCF, call that went out a year and a bit ago now. The lead research institution for this is the University of Strathclyde, specifically the National Manufacturing Institute Scotland. And as I previously said, Stephen is the PI on this and I'm project lead. So we kicked off this project in April of this year and we'll be running this through till December 2022. Looking at the agenda for today, I'll be giving you an update on the Mbas project, and then I'll be discussing what is hybrid manufacturing. We'll then have a technical presentation by DMG MORI, followed by a joint technical presentation by Hybrid Manufacturing Technologies and their UK reseller RAM Engineering. We'll then have a chance for a quick comfort break, and then we'll be joined by two of the engineers in Stephen's team to look at 2 case studies. We'll finish off the session by having a Ask the Experts digital panel discussion where you can put your questions to the presenters from today. So just quickly looking at who has supported this project and who will continue to support it, we've got a list of companies here from Scotland who work in different areas, but all ultimately have an interest and focus on additive manufacturing technologies. In terms of regional government, the Highlands and Islands Enterprise, which encompasses all the council regions that you can see there. The Glasgow City region, which encompasses these council areas in and around Glasgow. And lastly, Fife Council, who are headquartered in Glenrothes, who take up these broken up council areas as well. These are all the councils that pledge support towards the project to get it off the ground, but we're working across Scotland, so don't worry if you are located in an area that's not been mentioned here. In terms of industry and innovation support network, we've got SMAS, who are an offshoot of Scottish Enterprise, so that's the Scottish Manufacturing Advisory Service. There's Tom Gillespie and Ian Collison who are supporting this. From Scottish Engineering, we've got Julie Wright and John Campbell. And from SEED, who are working on a parallel cluster building project for the AMCF that I mentioned earlier, we have Ian Gibson. And finally, we have Dr. Abigail Hurd from the Knowledge Transfer Network. We have a series of webinars that will be delivered in 2021, and these are just a flavour of some of the topics that we're going to cover. So we've got design for additive manufacturing, wire arc additive manufacturing, CAM for additive manufacturing and hybrid additive manufacturing, qualification, validation, and certification for additive manufacturing, sustainability and resource efficiency for additive manufacturing, and lastly, integrating manufacturing to your business, so looking at cell and factory setup. These are not in any particular order, and the dates are to be confirmed, but these are what you'll see us advertising for 2021. An update of the project. We've so far to this day delivered over 40 hours worth of engagement sessions to Scottish SMEs. We've looked at 7 separate inquiries, and this is expanding every day actually. We've generated 6 direct supply chain link-ups between different companies and SMEs within Scotland. We've held 3 webinars, which has had a reach of over 250 people. Following today, this will now be boosted up to 4, and that outreach will have increased. We've created 3 AM specific support documents for SMEs as well. And in total, this is 8 companies that have been supported through the project thus far. But as I say, this is ever expanding daily. And in conclusion, there's 14 organizations and companies that are supporting this project activity. So there's some key criteria that make you eligible for working on this particular Mbas project, but if you don't fall into these categories, don't worry. As NMIS as a whole entity, we can work with you to figure out what your engineering challenge is. So as I say, for the Mbas project, to get free access to support, you need to be located in Scotland, be a registered SME, and also adhere to the horizontal themes set out by Scottish Enterprise, which if you follow this little web link here, you can find out more about that. The project itself is looking across all sectors in Scotland. We did a bit of sector analysis to think about what sectors we think that additive manufacturing could benefit most. But by no means are we limited to what you see in front of us. We'll work with any company that has a need or desire to look at additive manufacturing in more detail. So in terms of looking at the objectives of what we're trying to do with this project, it's really all about knowledge transfer. And that knowledge transfer is designed to allow companies to make the correct business, technology, and investment decisions in AM. So we're hoping to do this by de-risking innovation for companies, supporting them with their adoption of additive manufacturing, and really growing that Scottish supply chain. So by the end of working with us, we should be able to provide you with the confidence to invest in additive manufacturing processes and adopt these new technologies into your business. So what we understand is that additive manufacturing is a very complex thing once you start looking at it, and it's quite easy to get lost. And there's lots of questions about how do you actually integrate this within your business. So what we'll be able to do is give you that in-depth knowledge that are required to make these correct technology investments. We've got a deep understanding and a lot of expertise in additive, which we'll be able to communicate these and transfer this to your business. We've been working in this area for a long time now, so we understand the complexity of the supply chain, so we'll be able to break this down, simplify that to you. And lastly, looking at the facility that you would need to house additive manufacturing, the health and safety around this can be quite daunting. So we've gone through it. We've got all our lessons learned, and hopefully we'll be able to transfer this across to you in a very efficient manner. So essentially, what we're trying to get at is, if you do choose to work with us, you can adopt this whole work smarter, not harder approach. Essentially, let us do the heavy lifting for you, break down all the complexity, and give that to you in a way that's really kind of going to show benefit to your business. So there's 4 barriers to additive manufacturing that people always look at and think, can I achieve this, yes or no? And these are around suitability, so which processes or process match the engineering challenge that you have in front of you. Then looking at variability, people often hear that additive manufacturing can give you variable results. We can work with you to help you control that to gain your repeatable results. The reliability aspect of it. So you've now got your variability issues sorted, but how can we make those parts that you've generated align to industry standards? And then lastly, scalability. Understanding which technologies to invest in that will allow you to meet your current demand, but also looking ahead into the future to meet that projected demand as well. So what we've done is we've created a series of different support packages covering a range of different topics that will allow you to break down some of these barriers that I've mentioned there. So from the starting point of something like product suitability for additive manufacturing, all the way through to something like process validation. And we also had a series of awareness events which were originally planned to be delivered in person, where you could have come to AFRC, Mbas, and seen some of the technologies we have, maybe go to some of the companies within Scotland. But obviously, with the current situation that we're in and the current restrictions, we've decided to deliver this online for this moment in time, but we're really hoping by December 2022, we'll have been able to hold a number of events in person to show people the different technologies that we do have and what could benefit their business. So in terms of looking at something like how do I build a business case for additive manufacturing? If we look at that first step of looking at suitability, from the list that I just showed you there, these would be some of the support packages that we would pull together to help you come to that business case. So looking at product suitability, design for additive manufacturing, and then process selection. So that's at a support package level, but what does this look like as a step-by-step process? Well, we have a process for reviewing a product suitability for additive manufacturing. So there's a stage gate there where if at least one additive manufacturing process is deemed suitable, we can then move forward, ask you some more questions about what your engineering challenge is. And then we can move on to a design for additive manufacturing process where we're looking at the shortlisted technologies and generating some concepts around them. And then we can feed this into a process selection matrix that takes your handful of concepts and then pulls out the best one suited to you and suited to the manufacturing challenge. Then we can move to something like that people are more used to, a standard design for manufacture, where we've got one process, one design in mind, and move forward. And that's all the different constituent components that then build up to giving you that rich and detailed business case to decide whether we should start making some further investments and putting more effort into looking at additive manufacturing as a technology for your business. So if you look at the ISO ASTM joint standard for additive manufacturing, you'll see that it covers a range of different materials and they've got their own unique advantages and disadvantages, but they've split them out into these 7 families. And at Mbas, we'll be focusing on the following. So material jetting, material extrusion, powder bed fusion, and then we have an array of directed energy deposition technologies as well. As I said, this is simply put as 7 different families, but when you actually start to look at it, this is where the complexity creeps in. So for the purposes of today, we are looking at hybrid manufacturing using additive manufacturing, and more specifically, so machining as well as laser metal deposition in an open atmosphere. And the reason that we detail it out to this level is it then provides a context of what you would be working with and the materials and the limitations of what you're doing. So because we're working in an open atmosphere, that means we're restricted to non-reactive alloys. So things like cobalt, nickel, or steel alloys. And what this means is we cannot do is process materials like titanium or aluminium alloys. So looking at the capabilities in terms of additive manufacturing that we have at this moment in time at Mbas, we have a hybrid system ourselves, which you'll hear more about in this webinar today. We have metal powder bed fusion, and we have 2 wire arc processes. One is a plasma-based process, and the other is a gas metal arc-based process. And then looking at the polymers, we have industrial scale FDM and polyjetting, as well as some more desktop-based systems that you're possibly more used to seeing. So if we look at what is hybrid additive manufacturing, or hybrid manufacturing even, apologies, there's a lot of ambiguity out there. There's lots of different definitions that all say something slightly different. What we can do is look at those and pick out some really rich pieces of information within them. And what we can also do is rule certain things out. So for instance, that quote on the bottom left was suggesting that using coolant while doing machining is a hybrid process. For us, this would be considered to be completely out of scope. What we would refer to as hybrid manufacturing is the following definition. So using a single workstation, 2 or more processes, and lastly, integrated programming. When you bring all 3 of these elements together, this is what we would refer to as hybrid manufacturing. I won't talk through the details of this just now. I would invite you to go back and have a look at this on YouTube and read through line by line in more detail what we mean by this. But moving forward and looking more specifically at hybrid additive manufacturing, which we're talking about today, the definition that we've been working towards is the it seamlessly integrates additive manufacturing and subtractive technologies on a single platform. The synergy of integrated program allows for the harmonious interchange between processes throughout, enhancing their respective advantages and minimizing their disadvantages. But again, the previous rules apply, so it needs to be on this single workstation. What do we mean by additive manufacturing? So the ISO ASTM standard that I covered previously. Today specifically, we're looking at laser metal deposition, but there are other additive manufacturing processes that could be integrated to create a hybrid platform. And also subtractive manufacturing, so machining. These are the 2 that we've brought together on our platform and will be discussed by our industry partners today. And lastly, the integrated programming. This is what brings everything together and ensures that everything is working in synergy and working in harmony. So you have a true hybrid process occurring here. I'm now going to hand over to Terry Turner, the Business Development Manager for Additive Manufacturing at DMG MORI UK, and he'll be giving you a technical presentation with time allowed for at the end for questions should you have them. So Terry, I'm going to stop sharing my screen and now hand over to you. There we are, and just want to check your audio, Terry. Yep, your screen and audio is coming through perfectly, so I'm just going to pop myself on mute. And
thank you, Grant, and thank you to the Mbas team for the opportunity to join the session today. So as an introduction, firstly, my name's Terry Turner. I work for DMG MORI, and I head up our work in additive manufacturing in the UK and in Ireland. So that for this presentation today, I'll be covering where we are with hybrid additive manufacturing and where we see the benefits and applications for it arising going forward. So here's an overview of us as a company. So some of you may know that around 10 years ago, DMG and MORI joined forces to begin a cooperation that now positions us as the largest machine tool company in the world. So our core product, as you see here, is milling machines, turning machines, multitasking machines. So we're producing machinery across all of these machining disciplines. We have factory locations all over the world, and our headquarter factory locations are in Germany and in Japan. So essentially, our core is that we are a machine tool company, but building on these core machine tool technologies, we now have a focus on 3 strategic future fields. So they are automation of the machine tools that we sell. So we have an array of systems for our customers to also automate their workpiece or tool handling. The second of those is the digitization of the manufacturing process, driven mainly by our across-the-board control system that we now have called Celos. And the third of those strategic areas for us is additive manufacturing. So and particularly on the additive manufacturing side, we're actually working across 2 technology types. So these are both metal powder-based technologies, both using lasers to fuse material together, but very different to each other in terms of the way that they work. Both methods have their advantages, both have unique abilities to offer solutions to different manufacturing challenges. So with selective laser melting here on the left, also known as powder bed fusion, we're building parts layer by layer within a cubic build volume, using 1 or 2 lasers. And then with our hybrid DED solution that you see here on the right, we're using a powder nozzle building head within a 5-axis milling machine. So we have additive manufacturing in hybrid with 5-axis milling. So today's webinar focuses on hybrid manufacturing. So we're going to talk in a bit more detail specifically about the DED technology, how it works and what it actually offers us. So the diagram here in the bottom left shows that what we essentially have is a building tool that we can automatically load to the spindle of a 5-axis machining center. This then puts the hybrid machine in additive mode, if you like. The image in the top right shows how we actually deposit material. So we have a powder nozzle with a conical powder feed, conical powder flow through the nozzle. And then we have a central laser beam, which welds the powder material to the substrate under a shield of argon gas. So we're building parts as we interpolate the DED head around in the 5-axis machine in the same way that we would subtract material with milling tools. And the machines can automatically and quickly alternate between adding with the building head and subtracting with conventional milling tools. So the machines are actually based on our monoblock range of milling machines that are produced in Fronten in Germany. This combination of technologies is completely uncompromised in terms of the fact that we have a 5-axis machine tool that is very well established in the market. So all of that machining functionality, so cutting tool management, on machine measurement, cutting lubricant, and that experience that we have in machining and in 5-axis motion control, all of this is still there and uncompromised on a hybrid machine, with the additional availability of a building head. So everything is integrated into CAD/CAM as well. It's a turnkey solution. So our entire additive and subtractive process chain is driven in one place and controlled in the same way that a purely subtractive process would be. So our concept really is that we have a fully working, fully ready hybrid additive subtractive solution. So just to give an overview of what we offer in terms of systems, here are the machine variants that are offering a solution to working with, let's say, prismatic components. So these two machines they are identical in the way that they work, but are based on our smallest and largest monoblock 5-axis machines, the 65 and the 125. The 125 being released last year at the Formnext 2019 show in Frankfurt. So this takes our largest part diameter capability for hybrid manufacturing up to 1.25 meters, and the maximum weight that we can put on the table is 2,000 kilograms. Then here we have our turning center options for hybrid. So the 4,300 and the 6,600 machines. These are coming from our Iga factory in Japan, and offer a solution to longer and larger workpieces. The 6,600 is actually very new, and will be officially finalized in the spring of 2021. So just now going on to applications of the hybrid technology and where the benefits of it really lie. Firstly, we can talk about what it gives us in the context of when we manufacture new or spare parts. So one clear advantage is the fact that we're always building near-net shape features and parts. So whilst we still might finish machine surfaces, we're talking about an opportunity to cut costs on material stock itself, on cutting tool usage, and to offer an alternative to sourcing of expensive and perhaps long lead time castings and forgings. We can also add features onto parts, so we can start with a part and add something onto it. So that gives us the chance to consolidate on what our base geometry might have to look like when we're manufacturing different variants. So what that means is that we don't have to have all of the material there. Where it makes sense to, we can add it on within the machine. And then we're also talking about alternating processing. So if you take this example here with the image on the bottom left, with the cutting tool machining between blades, we can make that machining actually a lot easier for ourselves and cheaper for ourselves by only adding the perhaps awkward geometry later in the process. So thinking about using hybrid manufacturing in this way can really help us to consolidate on cutting tool assemblies and machining, which was perhaps inefficient previously. And as with all additive manufacturing processes, and what this image on the bottom right is showing, is that we're opening things up for the designer. So whereby what may be design favorable geometries that were perhaps not possible before, thanks to this hybrid process, we can now sort of allow the designer to make those things a reality. For example, can we create internal cavities? Can we build honeycomb structures like you see here, or can we produce perhaps thinner walls than what we could previously? So and the other clear application area that we find, and one that we've had a lot of success with, is repair. So whether that be with worn tooling components in casting and forming processes, or in high value end use parts such as blisks, where there's an economical advantage to repair and reuse high value parts, this hybrid process offers a one-hit solution. So in general, we're working with the idea of machining away worn or damaged areas, perhaps using touch probes within the machine to identify the areas of repair. Then we're building them back up, and then we're machining them back to final geometry. And here is an example that we have of a repair application with a customer of ours in Germany. So this is an automotive high pressure die casting tooling part, where previously was quite an unrepeatable, unreliable manual welding process, followed by a conventional milling machine to finish. What we now have is a controlled, one hit, digitally driven process with a time saving of 80%. The other advantage there is that once we have this controlled and digitally driven method of repair, driven through CAD/CAM, it's then easily transferable to other parts and other geometries. So functionally graded materials. So here's something that we're seeing more and more potential use for as we develop applications for the machines. The idea of dual material building of parts, or so-called functionally graded materials. So all of the machines that we offer have the ability to work with two material hoppers. So two material feeds that can be controlled all from the CAM system and into the NC code to locate two different materials in different areas of the part, or to transition from one material to another. So this can be a cost benefit, whereby we're putting the more expensive material only where we need it, rather than everywhere inside the part, or for reasons of mechanical or thermal performance, or for wear resistance. So as you can see here on the bottom right, we can actually interpolate the ratio of the two materials to quite a high degree of accuracy. And an example of this multi-material hybrid being used again in the die casting area, whereby we're fully building and machining a tooling insert in this example, but with a bronze core and with tool steel outer surfaces. So we start building in dual material fashion, then we interrupt the additive process with drilling of coolant channels, machining of the coolant channels, part way up the build, and then as we generate the part, what we're left with is a mold with quite significantly better tool life capability, better cycle time capability for the casting itself, due to the heat transfer property that the bronze gives us in conjunction with the coolant channels. Then talking again about application sectors for hybrid, we have customer cases whereby there's a business case arising from the ability to very quickly reproduce or repair parts where plant downtime is of a high level of importance because of cost. So with this type of machine in this kind of environment, we're also talking about being able to manufacture bespoke parts from scratch very quickly, versus casting and forging. So we're talking heat exchangers, pumps, valves, etc. So we do find that the business case for the technology can stack up very quickly when you compare it to, the realities of conventional manufacturing and the lead times that often gives you when you're sourcing legacy parts, producing tooling, going through quite difficult machining efforts, all of that costly and time-consuming factors can be significantly improved with hybrid manufacturing. So here's a nice example as well that we have in the oil and gas sector with a drilling head. So where rather than having a multi-machine workflow, we do everything in one platform. So again, it's this idea of do it in one. So in this example, we build up a 316 stainless steel body. We can then machine it. We can machine some coolant channels, and then changing the material, but going back to additive, we can add Inconel 718 cutting flutes. Then we can machine back that geometry before then finally applying a tungsten carbide coating. So this is all one machine, one hit, multi-material finished part. And interestingly there as well, if we employed our ultrasonic grinding spindles within the machine, which would also be possible, we can then finish grind the tungsten carbide coating as well. So this is an example where we're not just additive on one machine, then subtractive on another, or bringing that into one machine. We're actually taking advantage of the fact that we can alternate between additive and subtractive throughout the process. Then finally, I just wanted to share this poster that we had up at the EMO exhibition in 2019. So this shows a sample of customer applications that we have, and it's a good overview of the type of things that are possible with hybrid DED. So we have Sulzer pumps there in the top left. So they're using the machine to be able to optimize the design of their impellers, where they can now produce machine geometries that they couldn't before. We have Inner Schaeffler. Here they're producing tooling parts faster and with new innovations such as functionally graded material from a soft material to hard material point of view. The AMRC, here they're producing tooling parts. Sorry, the AMRC are producing aerospace parts for buy to fly ratio advantages. Now we have Toyota in the USA that they wrote a nice paper on this. They're using hybrid for all of their die and mold repair functionality. Then we have Helical 3D, a customer in Germany, whereby they're avoiding having to machine parts such as this one from solid. So advantages in cutting tool usage and in machining time. Then another interesting one is Korea Hydro Nuclear, whereby they're using a machine for spares and MRO. And then this example here on the right is actually a DMG MORI one, whereby we're using the hybrid technology to produce low volume parts for some of our other low volume specialized machines, in this case a laser texturing head. So we can easily change the geometry of that for specific applications. We can optimize the design, and we can manufacture perhaps what would be a multiple part build up in one part. So that concludes my presentation. I hope that was informative, and I'm happy to take any questions.
That was absolutely fantastic, Terry. Thanks for sharing that with us. I've actually had two private questions come across to me. The first one is asking, can a hybrid machine still do finish machining to the same level as your standard machine offerings?
Yeah, so the answer to that is absolutely yes. So as I said before, the machines are based on the monoblock 5-axis machines. They're one of the more common 5-axis machines that we sell. So all of that 5-axis expertise is still there. The machine in that sense is as it is. We do have customers that, you know, they will use the machine as a milling machine for 50% of the year, and then use the additive side of things when they need to, when they need to do a repair, or when it makes sense to use hybrid to manufacture parts. So yeah, you have a very established 5-axis milling machine at your disposal as well.
Perfect. Perfect. It's really useful to a lot of businesses out there. The other one is asking, what are the advantages of a Cartesian-based, so like a standard milling machine, versus having your hybrid based on robotic arms?
Yeah, I think with that, I mean, for a lot of applications, and certainly if you're talking aerospace, oil and gas, and those sorts of areas, you're looking for being able to control your weld essentially to a degree of repeatability, and to be able to know that what you produce is reproducible anywhere else in the machine. So you can, for example, develop let's say 316 stainless deposition parameters and know that that's going to work everywhere in the machine. So when you have a 5-axis milling machine, you know, positionally everywhere in the machine and the way that the machine moves, you know that you're producing the same thing. I don't think with robotics it's perhaps like that. You're perhaps teaching things in different areas, and the volumetric performance perhaps changes in different areas. So I think there's an advantage there when we're talking about how we can control the material that we actually achieve when we do it with a machine tool.
Okay, so accuracy and repeatability is more established using kind of standard Cartesian versus robotic. Got a question here from Steve Townley, and he's asking, how do the hybrid components compare in mechanical properties to make from solid castings, forgings, etc.? So
we're generally comparable with wrought material in general. There is some heat treatment often required. Things like hipping may be needed depending on the application, but in general we're getting very good as-built properties. And then on the tool steel side, we're achieving up to 63 HRC as built, and we can build. You know, another tool steel that we have is Ferro 55, and this is 55 Rockwell as built. You know, so there's not a compromise on material property as such. And if anything, we can actually control it. We can actually, because we're creating the material as well as the geometry, we can actually control and optimize what it is that we're building.
Okay, that's really interesting, and I suppose the key thing that you kind of discussed as well is with hybrid, you can unlock the kind of functional graded materials in a way that you just couldn't really do with any other manufacturing process. Yeah. Excellent. Okay, well, thank you very much, Terry. We'll catch back up with you for the panel session at the end.
Okay.
So now we're going to move on to hybrid manufacturing technologies. So we have Peter John Solomon, the applications manager for them. And they're also joined by Ross Milne, director for RAM Engineering and Tooling, who are the UK reseller for hybrid. So this will be a joint discussion. So Peter and Ross, I'm just going to stop sharing my screen and hand over to you.
There you go. How's that?
Yeah, that's coming through perfectly. I'm just going to pop myself on.
Great. I can see you still talking, but you're on mute. As Grant already mentioned, this will be a sort of a joint presentation. Got Ross as well from RAM Engineering and Tooling, who will chip in now and again on a couple of slides and have some items to share on the end. So briefly, I'll touch on a little bit of introduction to hybrid manufacturing technologies, or HMT. Go over the why. I'm grateful to Terry. I think he's already covered a little bit of the why hybrid, why add additive into machine tool. He's done a great job of that. And also go over the how. How do we do it in this context and in this case? A little bit about the company. It was founded fairly recently in 2012 off the back of a Innovate UK research project. We have offices in the UK and the US, and as you can see, there's about 50 systems installed worldwide. You can see a bunch of logos there from different customers, OEM partners we work with, and other research institutes that we have partnerships with. As Terry has already sort of showed you, we saw a very similar diagram to this on the right. This gives you the idea of what's happening in the nozzle in terms of laser metal deposition. Laser creates a multiple, powder's fed into that multiple, and we can start to deposit material. And what we've done in the hybrid context is on the left-hand side, we've taken that and we've brought it into a normal machine tool. So HMT really specializes in taking this DED, directed energy deposition, or in this case, laser metal deposition, and bringing this into conventional machine tools. Why do we want to do that? As I sort of already said, Terry's done a great job of saying why. So I don't want to rehash a lot of what he said, but I'll cover quickly of some of the very similar sort of application areas. Why do we want to do it? Repair and remanufacture is one. Oh, has that popped up? Are you just seeing my slide, or are you seeing some other images over it?
It looks like we're seeing your full slide.
Okay, that's good. Okay. So repair and remanufacture, you can see some examples there in the bottom left, impellers, blades. You've got the middle of the screen, you can see there's a pocket. You can see a slight difference in material. A pocket's been filled there. So castings, components where you need to, maybe there's a defect or big problems, you can machine it out, put the material back in. On the right-hand side, you can see a tooling insert, and that could be from various types of tooling, whether it's stamping or injection molding or press tools or even forging. So adding material onto the split line. So again, this is a application area why you want to bring LMD into a machine tool. This is a example. This is an end use customer. I asked for permission to share this slide. I can't show you any of the detail of the geometry, hence I've covered the top of the parts. They have 10,000 of these a year. You can see the kind of the parts are about 100 millimeter long, and it has a little feature on the end. When that feature wears out, they throw away the whole part, and that's about 10,000 a year get discarded. Now with hybrid manufacturing, that little feature on the end that gets worn, gets machined away, gets added back on, and then and it's finished again. And they can repeat this again and again. So here's a real life example of end use customer who pretty much full utilization, the machine through the year, applying remanufacture and salvaging parts, saving on material, saving on time, saving on cost. So a good example of why. Ross, I don't know if you want to chip in on this slide, if your internet's working for you. I'll give you a chance.
It's a good opportunity to everyone make fun of Wi-Fi in the Scottish Islands.
There we go.
Can you hear me now?
Yeah, that's you coming through now, Ross. Over to you.
Excellent. I can't actually see the slide, but I'm aware where he is. For some reason, it's disappeared at my end.
Oh, sorry.
It's all right. It's all right. Yeah, we're talking to quite a lot of different guys at the moment, guys and gals actually, about real life applications. And we're talking to a couple of guys in the forging industry who are looking to repair the forged tools. Obviously, there's certain areas within the forged tools that wear out more readily. So it's how to localize this by touching on, probing the parts, building it back up, and then machining it away within one machine rather than all the multiple processes and setups that they have to go through at the moment. Similarly, we're doing the same with the rail industry and the guys from the automotive industry. Interestingly, these are smaller companies who are looking to invest in this because they've realized that it doesn't have to cost an arm and a leg to retrofit this within machinery that they've already got. So they're looking at things like turbochargers and hubs, other component parts within cars. Likewise, mold tools and casting tools. And then on some of the larger projects, we're talking with oil industry clients about things like cladding on their master valve blocks, some valve ports, and side entry work, which is obviously very awkward to machine and to access. So it's good to see that there's real life applications actually opening up now.
Great. Thank you for that, Ross. So here's another example of repair and remanufacture. You've got those components on the right, you can see. And this is a sort of a comparison of, we had a scenario where the parts have been modified, so there's a new revision. You have 12 parts in stock. What do? Do you throw them all away and discard them and you make the new parts, the latest revision? Or can you modify them and bring them up to scratch by adding material on? If it's a metal off case, well, it's easy, but this case, it was a metal on. So the remake costs, so if you're going to throw away them and make a whole new batch, that's roughly what you're looking at. So you're looking at about £700 a piece and sort of 3 to 4 weeks. Or alternatively, you could modify them using hybrid. So using a 1mm laser spot, only about 2 grams of nickel, and additive time, so a deposition time of 30 seconds, 4.5 machining, you're really looking at about £20 per part. So that's considering as well the CAD CAM time, the setup, the processing time, and the overheads around that. So you can see that basically you salvage some parts and you've saved all that value that you would have had lost. And they're now up to spec into the latest revision. A great simple sort of case study showing the potential savings in some applications. Another area which Terry also touched on is coatings. So you can see various little parts here on the left-hand side. You can see an oil seal ring with an Inconel 718 in that groove. You can see a cross section. You can see the dissimilar materials there. On the middle to top, you can see just example of what the deposited metal looks like in its raw form. You got some aluminium bronze in the middle, Inconel on the right, and I think some stainless on the left. Again, in the bottom, you've got a nickel alloy that's been added onto the split line of an insert. And on the right side, you've got a sealing ring where a harder corrosion resistant material has been added onto just the diameter of that part. So again, it's a great example of being able to add material on in the same platform and finish it as well. Here's a real case study. So this is an example again of an end use customer. If you look on the right, you can see the bottom mold. And on very faintly, if you look on the split line, you can see a different material. That's a nickel alloy to give better hardness, corrosion, and heat resistance in the process. So before they adopted hybrid manufacturing, the process looked like this. They would take a casting, which was put in a machine tool, rough machine it. They would then take it out of the machine, heat it up to several hundred degrees, then put it in a robotic cell with a plasma transfer arc welding, add the nickel alloy into the split line, let the mold cool over several hours, then put it back in the machine and do the final machining. A lot of work in handling, a lot of work in progress, and longer processing times. Going and adopting the hybrid process, they could take the rough casting, stick it straight in the machine, rough it out, prepare the edge for laser metal deposition, add the material onto the split line, and then finish it in a much shorter time, sort of less than an hour. So you can see the potential, the savings there in terms of lead time, process simplification, and improved quality by using laser deposition instead of the PTA. And here's a few other parts which Ross sort of added, which I think you'd like to comment on.
Yeah, very, very similar to the process of the mold enhancement. In the oil industry, obviously, I'm based up here. We see a lot of applications in this area. Similar idea to the mold enhancement, where the guys are looking at the wear areas, but using the laser metal deposition and the accuracies of the machines, the CNC machines, we're in a position where the guys, it's not something new that they're doing, but they're altering the idea of what they have done in the past, i.e. they can aim the material at the exact right area and put on potentially less material to do a similar job. So at this stage, obviously, we're talking about coating a part and making its life longer. Again, similar with forged tools as well. There's a master tubing hanger, sorry, shown in the top right there. These lend themselves to this application pretty well, especially as we can take these back from service and then go into the repair stroke remanufacture style additive option as well. So by rights, you're designing the process in at the start, and you're also allowing yourself the repair towards the end of its life.
Marvelous, thank you very much. So we spoke about sort of repairing, manufacture, coating, and now adding features. And adding features, you can also kind of put in that section as growing parts. And with the nature of hybrid, you're always adding something onto something. So your substrate can become part of the part. If you look on the top right, you've got a component there. You can see a different material through the middle. That's stainless steel. So you started with a thin stainless steel plate, printed the sort of bronze material either side, and all in one setup, machined all four sides to get a complete finished component done in one setup. Really, you can't really make that in another way. On the bottom right, you can just see another example of simple features that have been made and printed. You've got the honeycomb on the left. On the top left as well, that part started off as a cylinder, and then those little blades were added on. So you've started with a smaller raw material, and you've added the little features on and then post machined it. So you've got quite a few advantages there. Just going over to just look at some of the comparison. If you made that conventionally against hybrid manufacture, if you did conventionally machined it, you would have had to start off with a bigger block of material. You would have machined off about 55 cubic centimeters, would have taken about 15 minutes. I mean, you can always argue about what cutters and how quickly you can rough the material off. But essentially that was 44% of your billet would have been machined away. Then you got 20 minutes to finishing time, to finishing your blade. So total was around 35 minutes. If you compare that to sort of a hybrid manufacturer approach, well, you don't have to remove all that material. You're only just doing a light, quick skim on the diameter, only 5 centimeters cubes removed. Then you're adding your features. That's only 3 minutes to build those little blades, 20 minutes finishing, and overall you end up quicker than the conventional manufacture. So you've saved on material, you saved on time, but the other thing importantly about adding features is you can add a performance enhancing material. So whether it's for hardness or toughness or corrosion resistance or wear, you can actually add something which is gives you the properties you want in a particular area. So it's just another quick example of how and why you'd want to apply this technology in a conventional machine tool. The next sort of step is how do we do it? Here's I'll pause it quickly. So now you can see normal conventional 3-axis machine tool. There's actually a rotary axis on there as well. You've got the laser metal deposition head in the spindle on a BT40 holder. We have a mechanism which comes down automatically, docks to the head. Once you're finished with the process, it goes away and you can tool change the head back into the auto tool changer, go back to milling cutter and continue machining. So really it's a seamless process. It doesn't compromise your machine at all. You can switch between adding and subtracting as easy as you would going from a roughing cutter to a finishing cutter. Okay. Now, so that's how an example of how it integrates into machine tool. This is a sort of a brief idea of the type of products available. On the left side, you've got the Ambit Flex, as you saw just in the previous video. That is on the spindle center line, and Flex, because it's flexible in the sense of you can have multiple heads and even different processes. So different size laser spots, different size nozzles, and even heads for inspection, even heads for removal. So it allows you to really seamlessly change between different nozzles and different laser spots as you would different milling cutters, because some jobs will need bigger laser spots and higher deposition rates. On the right side, you've got the Amber 1. So this is not spindle center line. This is we mounted typically onto the side of the spindle, but typically one nozzle, much simpler. You don't necessarily get all the flexibility you get of the Flex system. And that's just an example of the sort of heads you can get on the Flex system. And you can see physically the different nozzles, and they have different different laser spots. And even the one second from the left, We call that a 4-port nozzle in the sense of it's a different type of powder flow for different sort of applications. You also get the ambient multi because really you can have multiple heads with multiple technologies, and it can go on multiple platforms. So robots, gantries, machine tools, and also importantly, this one is really for multiple kilowatts. You're going 3, 4, 5 kilowatt range. So higher rate deposition, but you still get all the flexibility. But this one is not mounted on the spindle center line. It'll be again sort of on the side of the spindle. That's an example of the multi-system on a robot. That's an example in a gantry. And here's a little video showing the multi in a machine tool. If you manage to catch that, I'll show it again. I'll try pause it. Oh, there we go. So you can see the head comes down. Do your additive. When it's finished, the head gets put away. Moving away from metals just for one moment is if you have a different requirement, you also got the head that does polymer extrusion. And this is, I think, several orders of magnitude faster than normal FDM 3D printing, where you can go up sort of around 10 kilograms an hour of polymer can be extruded. Here on the right side, you can see it in a robot. On the left side, it's in a normal machine tool. You can process normal sort of pellets that you would from normal injection molding. You can see an example of some typical materials: ABS, carbon fiber nylon, fiberglass nylon, and the list goes on. Importantly, is that why would you want to put polymer extrusion in a machine tool? Well, one potential application is replacing the use of some structural parts which conventionally would have been made from aluminium, because this is high strength printing, really, the polymers that you can add. So it opens up some really potentially interesting applications for fixturing and work holding and so forth, and other structural parts that you might have used aluminium for. So we've sort of covered the why. We looked at some of the hardware and the products of the how. The next sort of part of the puzzle is, well, how are we controlling this all? And this is what we call our Amber core. This is the control unit, which houses the ancillary equipment as well that sits next to the machine. Inside this, you'll have your laser, your chillers, fume extraction, your powder hoppers, everything you need for the process. And this unit also controls the process and then interfaces and communicates with the machine. Here you can see the HMI. So the dashboard, which displays the parameters that are being used in the process, what's happening in the process, and all your parameters and stuff can be set and stored in here. So you've got the hardware, goes in the machine tool, and the Amber core then sort of controls it. The next piece of the puzzle is, well, how do we drive it? And this is just an example of some of the CAD/CAM providers who are offering DED or laser metal deposition modules inside their software. You've got EdgeCam from Hexagon, you have PowerMill from Autodesk, and you have Esprit as well. You also have others that I haven't mentioned, like Siemens NX. And I know even Fusion's starting to bring some of the DED toolpaths into there. So this kind of gives you, a maturity, really, where you have the CAD/CAM tools are there to start to drive it. We've got the hardware we can bring into the machine tools, and we've got the control to control the process. And this kind of gives the summary of that. You've got the idea and the design stage. This is where the sort of the AFRC can sort of come in with their project, the Mbas, and help people to contemplate, the design for AM and do they, someone thinks they might have an application or something which might suit, then, that's that part of the circle, the loop. We've got the CAD/CAM, as we've just seen. We've got the hardware where we can print and add the material in the machine tool. We've got the machine so we can finish it. And we've also, importantly, are able to inspect, because you are building something, you're adding material. So you want to check what you've added actually is fit for purpose. Some applications may not be necessary, but some will, and you need to have that inspection. You can also add some, use factory whiz for monitoring. So you've got to monitor your process, equipment, production. And this really closes the whole loop from your idea to controlling your process and having something that's repeatable and robust and adds value. And this is just a graphic to really show all those steps. On the right side, you've got internal cladding. So you go internal cladding and then your tool change, and in the middle, you go to external cladding. And then your tool change and you go to the bottom left and you do some machining. And then your tool change and you go to the left-hand side with an eddy current NDT and do some inspection. So this sort of helps you to close that loop in the machine tool and in the hybrid context. Just to give you a bit of an example of the practicalities of, you know, okay, you have something you need to make in a hybrid machine. What are some of the basic steps? The first step is to create, establish a bit of a process window. Establish good set of parameters. This is kind of very similar to selecting a milling cutter. You're going to choose, right, I've got a 10 mil milling cutter or a 6 mil milling cutter, and this is you know, suitable for your part. So you will use some parameters, test them out to create a bead that might be 2 mil wide and millimeter high. You need to know what those parameters produce so you can feed them into your CAD/CAM. Just the same as when you're going to do a milling path, you need to say, okay, this is a 10 mil cutter, and my step over is going to be this much, and this is my cut depth. Just the same, you need to have a set of parameters which produce something that you then feed into the CAD/CAM. That's the first step in the process. The next step really is, okay, you've got your part you want to make, and now you got to look at designing a preform and your additive toolpath planning. So you've got your two little simple parts there. The middle one with the fillet rads in the corners is what your final geometry is. That's what you want to have, okay? But in a very simple way, you now have to try and build something. You have to create additive paths to create that. But you'll end up with problems in the corners. You'll end up with holes because you are laying tracks next to each other, and you will most likely not fill those areas properly. So sometimes you don't have to always do this. You can design a simpler shape to create a simpler path, and you still build it to near net shape, and then you finish it. So in the top there, you can see that's been simplified. The fillet rads have been taken out. It creates a nice simpler shape. In the bottom left, you can then see a simulation of what I've actually then printed from that geometry, where in the inside, you can see the wall thickness is actually a little bit thicker. So I've made sure I have enough material so it's going to clean up on the inside with my fillet rads, and then get your final part. So it's a very simple workflow of just being able to, right, okay, establish your parameters, feed this into your CAD/CAM in terms of your step over, your layer height. You might have to design a slightly simpler geometry, maybe go back to some solid primitives, some simpler walls, simpler shapes that you can get your final part out of. You then print it and machine it. Right, and I think I'll hand over to Ross for this slide.
Yep. Thanks again, PJ. So out in the field, what we've noticed over the past few months and even the past couple of years, to be honest, is there's a bit of a reluctancy to adopt this type of technology. There seems to be a tendency of go with what you know. We know how to subtractive manufacture. So a lot of what we're doing at the moment is trying to get rid of that reluctance that's there. And this next slide, as we take you through it, we'll kind of show what we've done, what we've set up, what we've arranged to make sure that there's a loop there that's continuous. So basically, when we talk to customers, we've got a succinct set of questions for information gathering so that we can come back with a faster, more informed assessment of what people are, or what you're trying to do and whether the technology actually lends itself to that. So obviously working with hybrid, working with Mbas and Mbas process, we can qualify the work scope and give the advice back. If we move on from there to the quotation stage, we can obviously provide that. We can provide the equipment recommendation also. The good thing about hybrid manufacturing technologies is obviously you can buy a new machine and we can fit it to it. you can fit it to used machinery, or you can go with machinery that you already have, existing machinery within your own facility. Some cases, people are not even looking for the hybrid side of things, i.e. additive and subtractive. We're talking to a guy at the moment who has a machine that's not, it's a good machine, but it's not quite as accurate as the other machines. So he wants to make a dedicated machine. So by rights, we're reducing the limitations by having the flexibility of adding to many different platforms, many different types of machines. We work together, Hybrid and I, RAM Engineering, on the machine integration. Sometimes we may end up in the situation where the customer needs to get up and going faster than we can get the machine in. We can have the hybrid technology actually integrated with it. If that's the case, Hybrid actually have a subcontract center. So basically, we could start the manufacturing process for them down at our facility. Then, when the machine is ready, we can hand the whole thing over, turnkey application, lock, stock and barrel. But it doesn't stop there. Obviously, there's ongoing research and knowledge transfer. There's also qualification of the part. If it's the oil and gas industry, potentially you might want, it might need qualification through the OGTC. Obviously, there's ISO and ASTM processes to look at as well, but that's something that we're involved with Mbas and Hybrid as a group to make sure that the customer is getting the right thing at the end. There's no point in creating scrap, so we try to make sure that we're closing the loop, and it carries on after that. It's not one project. We're aware that things will move on with the times.
Great, thank you very much. As Ross sort of alluded to, the next sort of few slides I'll go through fairly quickly, but it shows, okay, well, how do we bring these products into machine tools? One option is retrofit. So retrofitting existing machine tools, any one of those products, the Ambit Flex, One, Multi, can all go into an existing machine. Then we provide the laser safeguarding, operator training, applications, so forth. Big question is, why would you want to retrofit? First main point, it's more cost effective, and it really does improve the business case for many more applications. When you think of the cost to work on a part or some applications, if you factor in, you know how much that machine is going to cost to run you an hour, but you've got an existing machine, you've added technology onto, all of a sudden, there's many more applications that you can start applying this technology to, and it really starts to make sense. The other one is you can use the platform that suits the part or family of parts. Okay, so don't have a bit of a compromise. You know you might have a certain range of parts. Put the technology on that machine that you really need, that suits maybe the accuracy or the type of part. The other one is, it's a smaller one, but existing users will be comfortable with machines. And also the hardware could be moved to another machine. So maybe initially you want to put it on an older existing machine, test it out, be comfortable, happy with the process, and then you can say, okay, well, let's move it to a new machine. And this is this is the retrofit option. The next option is delivered, and delivered is again adding one of those product offerings onto a new machine at HMT's facility, and then doing all the guarding, get everything sorted, and then sending the machine as new to the customer. The other option is OEM. So we have worked with a number of OEMs, and this is the sort of more fully integrated, optimized solution. Again, it's the same product offerings, the One, Multi, Flex. You can have some more advanced features because it's with an OEM of monitoring control. And again, operator and applications training can all be sort of provided. This is an example of some of the OEM machines. You've got the Oem machine in the middle, Sugino in the bottom left, 5-axis grind in the bottom middle, and a Hummel machine in the right. As Ross already mentioned, we spoke about advanced manufacture. So this is really to support people, to see the market, help people really to see real parts being made on real machines. Also for people to be able to come and get training. Also for people to, while they're waiting for a machine, their parts can get made, or but perhaps some people don't want to ever bring the process in-house and are happy for someone to take care of that for them. So this is another key part of the service really that's on offer. And I think we've sort of rattled through, but that sort of concludes what we had to say. Ross may have anything else to say, but other than that, I'd like to say thank you very much.
Yeah, I think we're bang on time there, so no, thank you.
Thank you very much, guys. That was hugely informative, and we have had a few questions in there, but I think actually as you went through your slides, you ended up answering a few of them. Conscious of time, so I'm going to just ask one question, and I'm going to take some of those questions that have been asked and put them into the general session at the end. And it's around what would you say an average sort of time is for a retrofit of an existing asset? I appreciate it will differ from machine to machine, but if somebody just wanted a ballpark figure of how long would this take, what would you say?
You're looking roughly around 2 weeks and maybe 3. And like you say, it really depends on the machine tool and the complexity of the guarding and the machine tool itself. So that gives you a rough idea.
Excellent. Okay. Well, thank you very much. And as I say, I'll pick up some of the rest of those questions and bring them through into the main session at the end. So we've just got time now for a 5-minute break. So get yourself a cup of tea, cup of coffee, have a wee stretch, and we'll catch back up in 5 minutes. And there's a little timer just along the bottom here, so you can check to see how long you've got left before we start up again. Thank you. Stretch, get myself a cup of tea. We're now going to move on to 2 case studies that were undertaken at Mbas. So first up, we have Connor McFadden, one of our manufacturing engineers. He has developed a hybrid demonstrator that he's going to talk through, and then we'll be followed on with Ryan Devine, one of the assistant manufacturing engineers in our team, and he is presenting a case study, digital, which was looking at remanufacturing forging dies. So Connor, I'm just going to hand over to you just now. So I'm going to stop sharing my screen and invite you to share yours. Yep, that's coming through, and I think possibly might still be on mute.
Yeah, thanks, Gant.
Yep, perfect. I'll just pop my video and microphone off and hand over to you.
Okay, thanks, Gant. So I'm going to speak to you today about a hybrid demonstrator project that we produced at the AFRC, which is one of the centres at Mbas. So it was a relatively small internal project looking at developing our capability while also showcasing some of the benefits of hybrid manufacturing by producing a demonstration component. So to start off with, we wanted to produce something that would be relevant to industry, something to show you why you might consider using hybrid manufacturing. To do that, we identified 2 areas we thought might be of interest, specifically cost and functionality. So in the previous presentations, you've already seen some of the benefits of cost, but from our case study, we wanted to start with a low-cost substrate, onto which we could then apply some high-performance materials, but only where they're required. So really, you're reducing all your initial material costs. We wanted to also show the functional benefit, and do this application of high-performance materials only where they're required. It does show how that using hybrid technology, you can take advantage of specific material properties in different areas within the one same component. So there's the functional benefits. We also have stock and machining efficiency benefits with hybrid manufacturing. Typically, you would need to buy stock that is larger than your finished component and then spend a whole lot of time and money machining half of that material away. With the hybrid process, we can get a lot closer to a near net shape, so we use less material, and even with the deposition, we still spend less time overall on the machine for machining. For our own capability development, we also wanted to vary the complexity as we go through the features. So for some of the features that you'll see, there are other ways of producing them, but we really just wanted a challenge for some of them. And it helped us learn how to program the machine and also find some of the limitations of our machine. So what did we end up with? We started off with some off-the-shelf 2-inch mild steel tube stock, so about as cheap a substrate as you can get. For the additive features, we used Metcoclad 21. That's a cobalt alloy, which has good impact and wear resistance. We've had some experience with this material before, as you'll see from my colleague Ryan's presentation when we get onto that. So we figured it was a good place to start, because we already had a pretty good parameter set for doing cladding with. We settled on 4 features with different levels of complexity. And they are a bearing face, which is the feature, the rightmost feature on it. So basically it's a small increase in diameter. A set of helical splines. And so these would be a sort of interlocking drive feature. We have a cam, which requires an offset buildup and would require a large billet. And then finally, we have a flange on the end. So for the manufacturing sequence, it's 4 distinct separate features, and we worked through them one by one. So we deposited, and then we machined, and then we deposited, and then we machined, and so on through each feature. The benefit of doing it this way, we started simple, and we increased the complexity as we moved along, and that lets us take the learning from each feature and read it over onto the next features as we progress through. Moving on to programming, we have a design for a component, and we now need to figure out how we actually make that component. So we used Siemens NX for all the operations in this project. They are a member at Mbas, so we have access to their software. Because we used Siemens NX for both the design and the manufacturing, it meant that we could quickly update geometry and add any kind of drive geometry or features that we needed, and quickly transfer that into manufacturing. If you've used NX before, you know it's a very flexible and capable CAM software. To use it, we configured our own post-processor, and we made sure that we were able to use machining operations or laser deposition operations. The software offers both, but we made sure that if we wanted to use the flexibility of the machining operations, we could still use those with the laser head. And now that we're a bit more advanced, so one of the features on this demonstrator actually did use the milling operations to create the deposition toolpaths, but now that we've used it for a while and have a better idea of how the software works, we're able to get everything that we need for additive from the deposition toolpaths. After programming, we simulated everything in VariCut. It's very important to check all your programs thoroughly through a simulation software before they go on the machine, especially if you're using a post-processor that hasn't been fully proven before. You want to make sure that you're not going to get any crashes. So using VariCut, we can simulate both the deposition and the machining, and it includes the deposited material in the model for the simulation. It also colors everything in so you can see exactly what tool's doing what. So the first feature is the most simple one. It's basically a cladding operation. So you might have seen cladding before. It's a fairly common application of this type of technology. We built this feature in 2 layers using a spiral pattern. So it's just a continuous helix that works its way along, steps up and then comes back. There was only 2 layers required to get the thickness that we need. We actually found that it built a lot more than we had initially expected. So I think we initially had 3 layers and we cut it down to 2. So here you can see how the operations were programmed in NX. If you've used it before, and as you can probably see from this, if you know how to use NX for milling, the additive operations are exactly the same kind of layout and structure. So very easy to pick up if you're familiar with the software. You do get the benefit of being able to visualize the component and the tool as well within the CAM software. So you can see everything all together. Once you have your part programmed in NX and you've output your NC code, we then put it through VariCut just to make sure everything is correct. I'll get onto that in just a second. So you can see the deposition. So VariCut is showing you exactly where the material is coming out and adding on. And then when you machine it, you'll see where you have material left. So it is simulating the subtraction of the deposited material, and it colors in each face so you can see exactly what's happening with each tool and quickly track back through your part and see what features have been produced by what tools. And finally, we have the end result of that operation. So fairly simple feature. So stepping over to the next one, we have a slightly more complex feature in helical splines. So we have 8 splines around the part. These are intended to be an example of sort of a hardwaring drive interface feature. We could have built these in the same way that we did the cladding. We could have just built a large diameter and machined it all the way, but that would defeat the purpose of using hybrid. We wanted to go near net. So we built all the splines individually. We use 3 layers with a zigzag strategy. So only 3 layers to build up the height, and you'll see the zigzag on the when I get onto the video of it. We lay down each layer diametrically opposed. So that meant we did layer 1 on one side of the part, and then layer 1 of spline 5 on the other side of the part. And that allows us to spread the heat throughout the component. And finally, when we machined it, we did cut into the substrate just a little bit to tidy it all up and make sure we had a bit of clearance on there. And it just shows that, you know, if you have got your hardwaring feature, your hardwaring material for the main feature, you can just use a cheap substrate for your clearance area. So again, we always run through Variability before we put it on the machine, just to make sure we're not going to have any expensive crashes. You can see the zigzag pattern here, so it's moving, the laser activates and moves back and forth. You can also see a small blob that appeared at the start. This was because of an auto clamp function on the rotary axes, and this is sort of typical of the kind of thing you might need to think about when you start integrating these systems and programming them. We've since managed to switch off that auto clamp function, but to get around it for this operation, we staggered the start point. It just goes back to what was said previously about the cam. You need to think about your strategy and how you're going to build each component. The total deposition time for this was only about 12 minutes, so it's quite time effective compared to if you were trying to machine it from a solid part. The next feature we have is a cam. So we have a 1 millimeter increase on the tube section all the way around the diameter. We then build a 9.8 millimeter high cam lobe on one side of it. So if you were to do this just from bar stock, you would need to have a 70 millimeter bar or larger to start turning that down and then milling to finish it off. The initial diameter increase was done exactly the same way the cladding was done, just a simple 2-layer spiral to build up. We then built up on one side with a zigzag pattern, so similar to what we did with the cam. The difference this time was we used an alternating zigzag, so we changed the direction each time on each layer. And finally, once we had produced the cam feature, we machined it and we engraved the AFRC logo on the side wall of the cam. That was just to show that with hybrid, you can do things that you wouldn't be able to do normally, because of the next operation, we build a flange in front of that face and you wouldn't have been able to access it. So you can see some footage of that spiral buildup initially, followed by the zigzag. So each layer on the zigzag, we switch between depositing radially around the part. So that's what you can see it's doing now, is the radial deposition, and moving axially along the length of the part. What we found is if you stick to a single direction during your buildup, you can get a bit of a fall away at the edges. But we've also found that you get a slight lump at the start and end of some of the longer toolpaths. So by combining those with the axial and radial alternation, you end up getting quite a clean vertical wall. You can see that pattern as it builds up on the video. So that was quite a few layers to build up this feature. It was an interesting program. And I gave a pretty good result, which you will see in just a minute. So in these pictures, you can see that zigzag pattern with the radial and axial deposition, and you can see the resulting machine components. So from the machine, you can see that it has all bonded together nicely and formed a nice solid material. So onto the final feature of this demonstrator component. We wanted to build a flange. Now this is the kind of thing that you would expect probably to have welded on as a plate. But if you were to turn it from bar stock, you would need to start with a 90mm bar and spend quite a long time turning it down. The challenge with this was mostly done for the challenge to us because it's such a high feature compared to its width. It's 20mm tall and only 8mm wide. So that meant there was quite a long build-up. We also had to tilt the part a little bit because the cam had built so high that we needed a bit of clearance so we didn't crash into it with the deposition head. So the first time we tried to run it, we tried it just as a single continuous path, building the full 20mm, which ran for quite some time and ended up, didn't turn out very well at all. It kind of came out quite conical. So we had to reassess our strategy and we decided to build in stages instead. So to overcome that initial 5-degree tilt, we started off by building 3mm tall to get to a point where we had a little bit of clearance. We then came along to skim the top of that. We built up the next section, which was 7.7mm tall. And then again, we machined it back to skim a flat face and deposited the final layer up to finished height. So you can see that in this video here. And again, as always, we run it through the simulation first. And in this bit of the video here, you'll see just how close we come to the cam and why we needed to have that 5-degree tilt. But it shows the advantage of having a laser system integrated into a 5-axis setup, is that you can get all these weird axis orientations. You might also notice one small issue that we found with this. So the first 3mm high build, when we come in with the milling cutter, it doesn't fully clean up. The cutter just barely scrapes the top of it. This taught us the importance of making sure we do a powder calibration before we run, because over the course of a few days, the flow rate seemed to drop a little bit. So now we're coming in for the second build up. This one built quite nicely. We corrected our flow rate and got everything running perfectly. And now we come in with a milling cutter and we skim that back just to make sure we've got a clean face to deposit on. And finally, we come in with the deposition head again, and we build up the remaining bulk of the diameter. You can see in this that it is still forming a sort of a conical shape. We believe that is an issue with the step over, or the step up rather, on the tool as it steps up in between the layers. It again uses a helical wraparound, and this is something we intend to address on follow-up projects for developing our strategies a bit further and make sure we can build more complex features. And here we have the finished part. So it's not quite perfect. We still have a little bit of learning to do, but most of the features have been fully realized. We have identified that we need to refine that strategy for some of the larger features that build a bit taller. And we have a follow-on project that is looking at some of these thin wall features and taller features. We also want to apply this onto forged components to lead on from the research done by the Forming Research Center where we work. So with that, I'm now going to hand you over to my colleague Ryan, who can show you some more applications on this system.
Just quickly want to take the opportunity to thank you, Connor. That was really informative. And I think the main takeaway from that is this is not without its challenges, but the Mbas, AFRC, and some of the industrial partners that we've had on today are always here to help support you with that and find a way to address these challenges. And just also want a quick thank you to Loki, the dog, there for his support. He sounded like he was very excited by your presentation, Connor. So,
I think he disagreed with some points, but yeah.
Oh, do you disagree? Okay, well, this is why he's on the technical board. And yeah, so as Connor said, we'll just hand over to Ryan now for his presentation. Thank you, Connor.
So, hi, good afternoon. My name's Ryan Devine, and I'm an Assistant Research and Development Engineer in the Machining and Additive team at Mbas. Today, I'd just like to talk to you about a recent project called Digital, which was related to the remanufacture of hot forging dies using hybrid additive manufacturing. So, the UK forging die market, which is valued at approximately £300 million, presented an opportunity for a low-cost additive manufacturing repair solution. And we were looking at the sort of benefits it could bring from a sustainability perspective, the cost savings, and then the improvements to the die life that it might bring. So part of the project was involving the AFRC gaining in-house additive manufacturing capability, which would be suitable for working on these hot forging dies. And as part of this, we had to then source suppliers for the retrofit, but also at the same time source a user of forging dies that we could work with collaboratively on it. So we identified that the capability most suited for us was laser metal deposition, and we were then looking to secure funding on this, and then again working with getting these industrial partners to work on the project with us. So the project itself was funded by Innovate UK, and we partnered with Hybrid Manufacturing Technologies, who you've heard from earlier today, and getting the LMD ambit system installed at the AFRC. We also worked with Mills Forging Limited of Coventry in England. They are a manufacturing company who work with hot forging dies, as that's their main use. So the project though as well, we worked with different partners as well who provided different services to us in their own areas of expertise. This was the flyer that we released early in the project to promote it. And you can see from here all the partners that were involved. So there's also ourselves, ATS, Hybrid, InSphere, Innovate UK, Mills Forging, and TTL as well. So yeah, as we've already mentioned today, the Hybrid Manufacturing Technologies installed their equipment into our old machining centre. So we had their Ambit S7 docking station and then LMD heads in the spindle. And here we can kind of see on the left this installation process happening to the machine at the FRC. And at this time, we also installed the Mick and fourth axis table to give us this more flexibility in the angles and the access to areas we can have by having this additional movement in the machine. And this was then the machine fully completed in the AFRC, ready to actually progress with the project. So one of the other critical aspects of the project was finding a material which satisfied all the criteria set out by our end user and what would be the best for them. So we created an initial metric that would allow us to screen through a large amount of materials and highlight it down to some of the key ones which we could then look at further. So we were looking at the sort of initial forging requirements, the mechanical properties, performance, processability, and then any other sort of economic factors which might be important. So we initially came down to quite a large range of materials, but including mainly cobalt-based alloys, different sort of steels, and some nickel-based alloys as well. So we would then take this list and evaluate some more of the critical areas in a lot more detail, primarily being the likes of the mechanical shock properties, the thermal expansion compatibility, as well as then other wear characteristics, just so that we could then score every material and work out what ones would be the most suited for using on the customer's die. So we constructed another sort of larger metric, looking at some more of these things and assigning scoring to different materials. And this would then allow us to work out what one would be the best for it. So we arrived at MecoClad 21, which this material is a cobalt-based hard-facing alloy, and its properties do make it quite ideal for hot forging die repair with this LMD technology. I've listed all the details of MecoClad 21 on this slide if it's something you're interested in and referring to later. So for developing our actual remanufacturing strategy, we had to consider quite a few factors, primarily being the die itself was made from an H13 tool steel, and we were going to be depositing MecoClad 21 powder. We were also looking to achieve a sort of deposition bead where we had a height to width ratio of about 2 to 1. And we then also had to look at the deposition pattern or the strategy for how we laid it down. And we really had two options here. We could either use a crosshatch strategy, where as you build up, each layer is rotated by 90 degrees, or you could be looking at a linear strategy, where each built up layer remains aligned with the previous layer. So to analyse what sort of strategies and settings would be best, we constructed a design of experiment with 4 off factors, these being laser power, powder flow rate, pattern, and feed rate, or feed rate sometimes otherwise known as laser scan rate. We also had 3 off responses that were identified, those being porosity, microhardness, and dilution. So we carried out this wide range of experiments and then a subsequent analysis on the samples produced in order to see what ones would satisfy all our requirements. From this, we saw that experimental run number 14 was the highest performing sample. It gave minimal porosity, which was ideal, and then minimal cracking as well. And it also maintained roughly this 2 to 1 ratio that we were aiming for. So this laid out the parameter set that we should be using when it comes to actually working on the final die. So just to summarize this, the sort of recipe that was produced for our LMD parameters involved using Clad 21 powder deposited at a rate of about 7 grams per minute. The laser spot size was 2 millimeters, and the laser power was 1200 watts. The feed rate or scan rate was 800 millimeters per minute. So the dies themselves are used by Mills Forging to produce parts for forestry vehicles, and this is done in their 1,000-ton hydraulic press out of a billet boron steel alloy. And what they would typically expect to see is about 1,300 parts as a maximum produced in their normal production conditions. So this essentially set the baseline target for our remanufactured die to meet, and this was our aim throughout the process. So just for visual here, this is a new die on the left, having just been manufactured before being put into any production runs at their facility. And then on the right is a used die, which has been removed from service, likely due to some areas on it wearing excessively, so the parts that were produced would no longer be within an acceptable tolerance. So working with Mills Forging on this, we identified the four main areas that were the most problematic for wear. These areas were wearing more than many other parts of the dies, and these were the parts which were deemed the most responsible for failed components. So we have here on the die, we have areas 1 and 4 highlighted, which is the left and right flashlands. This is essentially a mirror image of each other on each side. We have area 2, which is the flat part at the bottom of the cavity. And we have area 3 at the back, which is the sort of rear flashland or radius section. And for all these sections, the same sort of 3-stage hybrid additive manufacturing process was required in order to get it back to a sort of as new condition. We would machine away the worn areas, we would selectively additive in material at these points, and then we would machine that back to the final geometry. And then also at that point, ensuring it is within the original manufacturing tolerance. So other factors we had to consider was integrating a CAD/CAM system. And at this point, we then went with Siemens NX and with milling and additive licenses for this. We also had to ensure that we sourced appropriate tooling for the cutting of H13 and Clad 21. We also had to get then obviously the feeds and speeds for cutting of these materials and ensure that this setup was there as well. One other thing that we had done was we designed and then had manufactured a bespoke fixture for holding the die on our Niken 4th axis rotary table. This would give us access into hard to reach areas and complex bioid geometries by allowing us to tilt the die and rotate it to the desired position that we needed. This fixture also included some tooling ball datums on it. These tooling ball datums were used for aligning laser scanning, which would allow for adaptive wear detection on the key areas. So from this, we identified that for flashlands 1 and 4, we had to machine to about 1.5 millimeters deep in order to remove any worn and damaged areas from the surface. Similarly at flashland 3, we also had to machine to about 1.5 millimeters deep. However, for the cavity in section 2, that only had to be machined to about 0.5 millimeters deep, and that's in that place. So for looking at then the reconstruction of the die, the deposition part with LMD, for flashlands 1 and 4, they were essentially mirror images of each other, 3 layers at about 0.7 millimeters high each. We had a 1.2 millimeter step over between paths, and we also had a 1 millimeter path overhang. And this was just to ensure that we built up a sufficient amount of material that it could then be cut back to nice final geometry that was within all the tolerances required. Flashland 3, however, it had quite complex geometry in that area. It was quite a difficult access to reach as well. So it required a bit of a unique solution for tackling it. So we split it into 2 stages, and this was mirrored left and right on each side of the radius. What we did first, and this is kind of indicated in the top image in the slide, is we built up the incline section first. We then came in and machined that flat before then redepositing on the top, and that would then allow us to fully repair that area to a satisfactory quality. We also had a similar sort of parameter set to what we used in Flashland 1 and 4, with 3 layers, 0.7 millimeters per layer, and the same sort of overhang and step over. For the cavity flat area, we only then required 2 layers because it was a shallower cutout initially, same layer height and overhang step over. However, this area also still had some technical challenges with it, and that we had to ensure a really smooth transition between the H13 die and the MetcoClad 21 areas. So the way we achieved this was we did our initial deposit on, we then machined that flat and ran then an additional bead around the outside of the area. And this has essentially created a sort of picture frame effect. We would then machine this flat again, and this gave a much smoother transition and blend between the 2 materials. So I'll now just show you a short video of the repair in action. This is after any sort of initial machining. We are going to the docking stage, and now we are depositing material in area 3, the flashland at the back, and this is working on the inclined section. Then after having done one side, we rotate it round to do the mirror image of it as part of our strategy here. One other thing that we have during the process is the live data readout on the controller. And this would let us monitor many factors about the machine and just ensure we have full control over the process. We're now moving on to the repair on Flashland 1. Now we're undocking, ready to tool change over to a milling tool and start the machining process. So this is us coming in to machine Flashland 1 to its final geometry. And now finally machining the flat on cavity area 2 to its final geometry, ensuring that smooth blend between the 2 materials. So here are a couple of images of the die at different stages of the repair process. On the left, we have a die just after all the additive process has been carried out. So the process has been paused halfway through to allow a picture to be taken when you can just see all the additive buildup areas. And on the right, you have a die that has been through the entire process with all the areas machined back and within the final tolerance. And at this point, this die is ready to go back into production trials at Mills Forgings site. So for the production trials at Mills Forging, they had a 1,000 ton hydraulic press, and they would normally expect to see 1,300 parts out of a new die. And our die just ran in the exact same production conditions that would normally happen. And this was then carried out at their centre. So these pictures were taken in their press after the die had produced about 900 parts. At this point in time, the dies were showing really very little wear on the MetcoClad 21 areas, and the performance on them was going really well. It was really high performing at that point. So this was really good for us to see at this quite far into what would be a production run, the dies are still performing really well. So just for reference, a new die would normally produce the 1300 parts. Our die went into service as normal, ran its 1300 parts, but then we were able to get an additional 1400 parts out of that die for a total of 2700. This gave us a 108% increase in life. So with that, it obviously brings with a good number of sustainability benefits and cost savings as well. So one of the other things we experienced was actually less wear on these MetcoClad 21 areas, which shows that the benefits could also be applied to a design for remanufacture, where you can do these key areas in this sort of hybrid process to ensure that you actually get less wear on the die. We also had no production issues reported by the customer whilst it was in service. So just to sum up, from the project, we were able to say that the LMD process is ideal for hot forging die remanufacture, particularly when it's in this hybrid additive manufacturing platform where everything can be done in one machine in one process. There's the capability to work on these complex geometries, and the die life improvements are really beneficial for the customer because they don't need to buy new dies after 1300 parts. They can extend that life to a total of 2700. So it just shows the potential for the commercialization of this technology is really evident. So if you've got any questions, please feel free to get in touch with myself or the team. Thank you.
Thank you very much, Ryan. That was absolutely fantastic, really in depth as well, showing everybody the kind of benefits are possible with this technology. So we're now going to move on to the digital panel Q&A session. If I can just get my screen back up here for everyone. What I would say just before we move on to that is for inquiries and more information about what you've seen from AFRC and Mbas point of view, you can reach out to us on our website. But similarly, two of our business development executives, Alistair McDonough and Barry McGee, their email addresses are listed here for you. So as I said, now moving on to the Ask the Experts session. So we've got Stephen Fitzpatrick, who heads up our additive and machining team here at Mbas. And then we're joined again by Terry, Peter John Solomon and Ross Milne from the earlier presentations. So what we've done is we've taken questions that have been asked throughout the session and I've put them into this section here. So we'll go through these one by one and I'll ask the different people their thoughts and opinions on this. And once we've got through those three questions, if we still have some time, I'll open the floor at that point. So question that was asked is hybrid AM compatible with mill turn machining? And I think I'll go to Terry on that one just firstly. If you're able to unmute yourself and provide a response, please.
Certainly is compatible, yeah. I mean, one thing that we see often with turn mill parts is that you have cylindrical parts with features on them, and what you have to do is mill most of the cylindrical features because you have a feature in the way. So with hybrid on a mill turn platform, what it allows us to do is to pre-turn the cylindrical features either on a lathe or on a turn mill 5-axis machine, and then start adding the features that perhaps are making the turning awkward. So absolutely compatible. Like I said before, milling, turning, coolant, management of cutting tools is all possible in our machine. So absolutely, yeah.
Okay, so just to confirm on that one, you offer a mill turn hybrid machine?
Yeah, so the 65 3D hybrid comes with an FD table, which is a mill turn table, so we can get up to 800 RPM on that. So it's a prismatic trunnion-based 5-axis machine, but whereby we can lock a turning tool in the milling spindle and do turning. And then, as you saw on my slides, we also have the 4300 and the 6600 turn mill-based machines with the additive heads as well.
Excellent. Okay, thanks for that. So a few options there. So I'll just tweak the question slightly for Ross and Peter John and ask them, could you retrofit an existing mill turn to incorporate your hybrid technology?
Yeah, we can do. If you looked at one of the examples of the OEM machines, there was the Hummel machine, which is a mill turn machine, and that's with an OEM, and that's the flex system, so spindle center line, and also likewise you'll be able to do that to existing machine. Yeah, that's the short answer.
Brilliant. Okay, so you've got an off-the-shelf and a retrofit solution for that question then.
Mm-hmm.
Excellent. Okay, thank you very much. I don't think we need to ask Stephen on that one, so I'll move on to the next one, and I'll go straight back to you, Peter. And we had been asked, is heat treatment ever necessary with hybrid parts?
I think that the first thing I would say is that the whole sort of DED or LMD process in a machine tool is just another tool that works for some applications, and it's another tool in the box in manufacturing. It's definitely not going to be the everything for everybody. So we shouldn't try and do that as well. So there's going to be some applications, some parts where it doesn't make sense to try and push it down the hybrid route. And sometimes that may be parts that may need a lot of heat treatment. So you'll be better with a single cell. So do DED on a standalone cell, but that could be a hybrid cell, and maybe you just do DED on it, and then you move it out and heat treat it and you machine it on another machine. So it's just trying to be quite practical about the approach, and not trying to think that there's a silver bullet for everything. So yes, heat treatment could be necessary, but you'll probably try the applications that are probably going to make more sense are the ones that you don't. But there may be applications that you want to be able to build something, take it out of the machine, heat treat it, put it back in and machine it. Absolutely. It's just you have to look on a case-by-case basis. I don't know if Ross has anything to add to that, but
no, I totally agreed. Horses for courses. But to be fair, if you're looking at these applications beforehand, we would work that out before you got to the point in which you were actually needing to do any heat treatment.
Brilliant. Thank you, guys. And Terry, what's your take on that one?
I would agree with Peter, John, and Ross on that. In that it's a case of looking at the application and you see whether or not it makes sense. I mean, heat treatment will sometimes be necessary. One advantage of hybrid is that if it's needed for stress relief, then we can perhaps manage that with the process. Whereby if we do get distortion, we can manage the stock control, if you like, with what we're adding and subtracting, and do it that way. So yeah, is it ever necessary? It can be, but I wouldn't think about it being any more necessary than what it is for machining things from solid. Yeah,
and I think that's a good point to make, that additive isn't a completely a kind of panacea. It's not going to solve all your problems. It's another tool in the toolkit, and should be treated as such. Stephen, would you like to provide some input on that one?
Yeah, no problem. So I guess we've seen, various applications today, remanufacture, feature addition, coatings, where the heat treatment hasn't been required. And, that's one of the key advantages. If you can take the deposition process to its final condition, meaning no further heat treatment, then, that opens up a lot of opportunities for hybrid and productivity opportunities. Like Terry mentioned, doing it in one. If heat treatment is required, and this is something that you've been doing in your PhD grant, is you can look at things like localized heat treatment, particularly for things like remanufacturing, where there's only a small section of the component that needs to be heat treated. There's only a small area that you're maybe repairing, or a small area or feature that you're adding onto. There is opportunity to perhaps use the laser either within the existing platform or another laser to actually locally heat treat there. So that's more of a research and development opportunity, and something that we plan to look at going forward.
Thanks, Stephen. I was going to kind of leave this open to you guys, and I was just going to compare. But Stephen's kind of set me up there to expand on that. And yeah, this is something I have been looking at in my PhD, and that's how do you actually use the tools that you have in front of you to overcome some of these challenges. So something I have looked at is what you can do is defocus the laser beam and actually stop the powder flow, and use that as a in-process heat treatment. So you can actually selectively look at relieving residual stresses in the depositions that you've created, as opposed to taking the entire component and putting it into a furnace. This is especially important when you start to talk about the example that Ryan had showed there. So a forging die where 95% of the part is already within geometric tolerances. If you're then to put that into a furnace, the distortion would then bring that out of kilter. So it's all about being very adaptive and clever with what you have in front of you and finding the solution to do that. We had been asked earlier on as well about what are the barriers to build rates and what are future plans to improve this. And I think this is actually a really good question, and it was actually asked during Terry's one, but I held back on it because I thought it would be a nice one to open up to everyone to provide an answer on that. So Terry, given it was your question, I'll put it to you first.
So currently for build rate, we're talking perhaps 1 kilogram per hour in stainless steel as a ballpark. We do have, so on the prismatic machines, the 65 and the 125, we have a 3 millimeter laser spot as a standard. And then we have a smaller one, a 1.6. So you use either or for the application. We find that the 3 mil one is a good all rounder for different applications. But then obviously build rate is something that we will try and improve as we go forward. On the turning center machines, we have laser spots that are more square, so we can clad cylindrical parts a little bit faster there. But it's something that we'll develop as we go forward to try and increase that.
Excellent, thank you very much. And Ross and Peter John, could you provide us an answer on that one?
Yeah, it is a good question, and it really is application specific, where if you have a small little part, the last thing you want to do is put a whole bunch of energy and heat into it, especially if it's a small little blade or something. Then you want to actually reduce your deposition rate to get the quality. But again, Terry quoted a good number around kilogram an hour. In reality, which is a good ballpark for around a kilowatt or kilowatt and a half laser power. If you're going to go up to 2, 3, 4 kilowatts that you can on the multi-system, then you can go to 3-4 kilograms an hour. But now you're putting in a ton of energy and a ton of heat into the part, so it has to be proportional to what you're doing. Is it a really big substrate? Is it a big shaft? Is it a big tool? Can it absorb? It's all about the thermodynamics. So it's less about yes, you can increase the deposition rate and you can go up to several kilograms an hour, but you're going to find very few parts you want to do it on. If that makes sense.
Yeah, no, it makes perfect sense. And yeah, I think that's a good way to think about it. It's all about a balance of application versus what you're trying to achieve and the limitations of the technology. And there's always going to be a sweet spot for each technology, and that's really where your business case is for selecting that. Stephen, do you want to provide us an answer?
Yeah, I think the guys have covered most of it, but it is all very dependent on application. You can go to a larger spot size, a higher power laser, or even change the shape of the spot to give you more productivity, but that does have a trade-off in terms of the energy input that you're putting into the process. So yeah, it is all about application. Maybe that's a research challenge for us, you know, how you maintain the heat input but increase the deposition efficiency.
Excellent. Okay, and I've had one more question that I'm going to take from the open floor, and then we'll probably round up everything. And we've been asked, does coolant need to be cleared after a machining step prior to the next DED step? And Stephen, I'm going to go straight back to you and ask you immediately.
Okay, thank you. So, you know, I guess this is something that we had a concern about, you know, when we brought in the hybrid system. So far, we haven't found any detrimental effect when we've been carrying out deposition, then machining, and then deposition again. Obviously, when we start off with a substrate which is, you know, been ground and been cleaned sufficiently. But generally, we're not seeing any issues with that when we're looking at when we're cutting it up for metallurgical purposes.
Yeah, can I comment on that, Grant?
Yeah, sure. Go straight to you.
Yeah, I agree with what Stephen said. What we've seen is, if you've done some wet machining, and if the parts then for some reason been left overnight and all the coolant's dried and you're left with a oily residue, then you're going to see we've seen some issues. But if you've done some fresh machining, the coolant's there and it's kind of just sort of freshly dispersed off the surface, and you do some cladding, the laser sort of vaporizes whatever the sort of contamination's there. And we, like Stephen said, we haven't seen any issues there. In fact, we did a study with the MTC, the Manufacturing Technology Center, and we had a plate with coolant on, left the coolant on, and then started cladding. And the gases from the process actually dispersed the coolant and then deposited the material. And we saw no difference from that to a part that had been cleaned with IPA solvent. So for me, it's really, if it's a thick, oily residue that's going to be left behind, then you've got an issue. Likewise, if you've got a puddle in the middle of your part, you're not going to clad into your puddle. It's where coolant's been dispersed.
Brilliant. I'm just going to expand on that quickly before I'll go to Terry on that one. And again, this is where, like I say, you can be very clever and use the tools that you have there. So as Peter highlighted at the end there, so if you've got a puddle of coolant, so like you saw in the remanufacture that Ryan presented, what you can do obviously is use the turntable to tilt it, so to pour that out. But also, as Peter highlighted with the gas, if you're really, really worried about having coolant on feature before you use your laser metal deposition, you could do two things. One would be you could turn the gas flow on just itself to try and maneuver as much of that away. But then you possibly also could look at, again, defocusing the laser beam to try and clear some of that. That you would need to do some research into understanding the mechanisms. But as Peter said, the studies they've done with the MTC have kind of highlighted what is and what is not required and the benefits and advantages of that. Terry, what would you like to expand on that with?
Yeah, I think as you've all said, it often doesn't throw up any metallurgical problems, but as with any high value manufacturing, you're generally thinking, well, variability is the enemy in any way. So you use the tools that you've got there, whether that's through spindle air blast through an empty tool holder as a qualification of your substrate, can be worth doing, just so you know that you're always building on the same thing and it doesn't take too long. So I don't think it's an issue. It's just something that you manage as you develop your process.
Excellent. So I think we've done a really good job there in answering all these questions. So I was just firstly wanting to thank those who've presented today. So Terry from MG, thank you very much yourself, and Peter John and Ross from Hybrid and RAM Engineering respectively, thank you very much. And also thanks to Ryan and Connor from Mbas. There's 2 great case studies that you've shown us there. So if you've got any further questions that you're wanting to reach out specifically to myself and Stephen, here are our email addresses. In the chat, Terry, Peter and Ross have all provided their email addresses and links to various different things that you can check out for further information. But as I mentioned earlier, if you've got a general inquiry or you don't fit into this Scottish SME category for the Mbas project, by all means, please get in touch with us at the National Manufacturing Institute, and we'll do our best to get back to you as quick as possible and get you the information that you need. And just on that, I'm going to sign off there, and thank you very much everybody for your attendance, and this webinar will be made available on our YouTube channel in the coming weeks. Thank you.